So the final step in our regular expression pattern matching algorithm is to construct the non-deterministic finite automaton. So how do we go ahead and do that? And this is an integral part of the algorithm, but we've pretty much got all the pieces. But really what makes it intricate is that it's an illustration of what a programming language has to do when trying to understand your programming, what your program does. What we need to do is somehow understand what's in the regular expression and then take that information and use it to build the machine. Now that's what's parsing, that's called parsing, to try to figure out the structure of your program or regular expression and then do something with it. And this is a simple example of that, but useful as well. So the first thing it's clear what to do. So we're going to have one state per character, as we talked about before, so that's easy to set up. And then the match transition edges, if a state contains a character in the alphabet, we just put in a match transition to the next state. And actually that's implicit in our algorithm. So now what about other things? Well, if we have it for any parenthesis we find, we'll just put in an epsilon transition to the next state. So our machines all have that. Now closure is the one that has quite a bit of action. So for every star, and let's look at the one that is just a one character closure. So we have a single character closure, so this is a star. And what we need is epsilon transitions for the star that allow the machine to go and pick up, well, there has to be an epsilon transition that goes out to the star to cover the case that we have 0 matches. And then after 0, then we want to go back to have as many matches as we want before taking take the match transition. We want to be able to go back and match as many as we want before going out to the next. So for star, we have to add 3 epsilon transitions. The one that goes, if you have a character in I and a star in I+1, you have to add these edges going both ways, and then an edge going out to the next character to get out of the star. And that works also if there's a closure involving parentheses. If the character before the star is a parenthesis, then we want to add the same kind of mechanism. From the parenthesis, go out and skip the whole thing to cover the 0 match case, or go back and match as many times as we need to match, and then finally go out. So there's 3 edges that have to be added for each star when you find it, and it's well defined what they are. And then or, there's 2 epsilon transition edges that we have to add, and that is to allow the machine to skip the first part of the expression and do the second, or to do the first part of the expression and skip the second. So if we keep track of where the left parenthesis is when we end the or operator, when we hit the right parenthesis, we have all the information that we need in order to be able to add those 2 edges. So those are the edges that we have to put together to build the NFA, and the trick is keeping track of the information of where the previous operators are, particularly since parentheses can be nested. But this is not that difficult to do because we have a mechanism for doing that, how to remember where the left parentheses are in the or, and that's to maintain a push-down stack. And so the algorithm is to push left parentheses in ors onto the stack, and then when we hit right parenthesis, then we can pop the corresponding left parenthesis and maybe the or And that gives us all the information that we need to add the epsilon transition edges. And so the stack takes care of the nesting of the parentheses. And when you think about it, this is a very natural mechanism to use, very similar to the early programs that we wrote using Dijkstra's algorithm for arithmetic expressions. So let's look at a demo, and you'll see how that works. So we're going to build the machine corresponding to this regular expression, and it's the one that we've been working with. So what we do is just go from left to right through the regular expression and take the appropriate action for each character. So for left parenthesis, there's always an epsilon transition from left parenthesis to the next state. And then the other thing is we remember that left parenthesis on the pushdown stack. So we put the index 0 onto the stack. So now we get another left parenthesis. Again, we put the epsilon transition on, and we push that 1 onto the stack. So now if we have an alphabet symbol, what we need to do is add the match transition to the next state. And then there's a couple of ways to do this, but one easy way in this case is to just look for the star. And if you see that the next one is a star, then you've got everything you need for the epsilon transitions. So in this case, the next one is a star, so we'll add those epsilon transitions from from 2 to 3 and from 3 to 2. And adding epsilon transitions, that's just adding edges to the die graph. Then we closure, that just takes us to the next state, and we took care of the other two earlier. Now we have an alphabet symbol, that's the B, so we just put in the transition to the next state. Now we have an OR. All we do for an OR is put it on the stack. And now we've got, for A, we got the match transition. For C, we have the match transition. And now we have the first right parenthesis. This right parenthesis, so first thing we do is add an epsilon transition over to the next state. But then we go to the pushdown stack and we pop. And if the thing at the top of the stack is an OR, then that's one piece of information that we need. The other piece of information we need is the position of the corresponding left parenthesis, and that'll be the next thing on the stack. So we add the transition, we pop the OR off the stack, and we pop the 1 off the stack, and that gives us the information that we need to put in the epsilon transitions. We're at stage 8, we put 1 from the OR to 8, and then we put 1 from the 1 to the OR plus 1. That's what we need to do. And look for a star, same way as we did for one character. Now in this case, we have no star, so we just do find an alphabet symbol, we add the match transition, and now we have the right parenthesis, and so we pop the corresponding left parenthesis, and it's not an OR, so in this case there's nothing to do except do the epsilon transition to the accept state. So that's the process for each character in the regular expression. It's well defined what we do. Left parentheses and ORs we put onto the stack. Characters, we do the match transitions. In right parenthesis we do a pop, and if it's an OR, put in the OR transitions. Otherwise we do the lookahead to check for the star. And that's the demo of the construction for non-deterministic finite state automata. So it's actually a remarkably simple process that we figured out what to do for each character in the regular expression. And this is the second part of the regular expression pattern matching algorithm, which is constructing the NFA. And again, it's remarkably little code. So it's a routine that builds the epsilon transitions. This is as part of the NFA, so it's got the regular expression as an instance variable to refer to, and it's going to build a new digraph with one state, one extra state, the except state, m plus 1 if the regular expression has m characters. And then we maintain a stack, which is just integers. And for every character in a regular expression, we do the processing that we just described. If it's a left parenthesis or an or, we just put it onto the stack, and that's it. If it's a right parenthesis, then we pop. If that pop is an or, then we put in the two edges to skip the or, and otherwise we look ahead and do the closure exactly as described. And if it's any one of the metal symbols, we just put in an epsilon transition to the next edge. Again, remarkably little code to go ahead and construct the NFA for a given regular expression. And so the final step is the analysis. That's going to take time and space proportional to m, and that's immediate because for every character we do at most of 2 stack operations and add at most 3 epsilon transitions, and this is a generous upper bound. Time and space proportional to the number of characters in the regular expression. So that's how we get the NFA constructed.